Okay, welcome to the next part. So in this part, the next important term, that is the next important term is oxidation state. Oxidation state. Okay. So let me define what is oxidation state. You know what is oxidation state because you are familiar with the redox reaction. So here the oxidation state of central metal, that is the next point, oxidation state of central metal. So what is actually the oxidation state of central metal means? It is the residual charge possessed by a metal by the proper treatment of charges of counterion and ligands. Okay, so residual charge on metal, residual charge on metal, that is said to be oxidation state. Okay, fine. And the residual charge of metal can be calculated by considering the charge of ligands, that you know what are the charges of ligands, and also the charges of counterion. Okay, let me give some examples for that. If I have a molecule Cr H2O 6 times all of Cl3. Okay, one of the important section is to find the nomenclature. To identify the nomenclature of a coordination compound. That is one part. Okay, so you have, if you want to attempt the question regarding the nomenclature, you have to know you should be able to find the oxidation state of central metal, because in every nomenclature there is a method, that representation of oxidation state of central metal on in a parenthesis. Okay, so the method for finding oxidation state is very important. Okay, fine. So CrH2O 6 times Cl3. Fine. So how can we find the oxidation state of chromium? We all know that this chromium offers -1 into 3, that's equal -3. Right? This counterion chromium offers -1 into 3, that's equal -3. If so, the entity should offer a +3. If this counterion offers a charge of -3, then the coordination sphere should offer the charge of +3. Ready? Then only it becomes neutral, right? So there are three chlorines, where 3 chlorines offers -3. So that is the counterion. What is the charge of counterion? Exactly the opposite charge with the same magnitude will be offered by the Hall coordination sphere. So the Hall coordination sphere offers a charge of +3. And we all know that the +3 charge is a sum of charges of your central atom and ligands. The whole charge of the coordination sphere is the sum of charges of what? Central atom and ligand, which is enclosed in the coordination sphere. Fine. So it is clear that your chromium charges of chromium plus aqua H2O 6 times is 0. Sorry, +3. And we already know that the charge of H2 is a neutral ligand, right? Yes or no? Yes. So H2 is a neutral ligand. So charge of H2 is 0. Ready? So 0 into 6 means 0. So there is no charge offered by your H2O, which means that the +3, which is exactly offered by the chromium. Ready? So this +3, the charge of the whole entity +3, which is exactly offered by your chromium. So it is clear that the oxidation state of chromium is +3. Is it okay? Fine. I'll give you next example. If I have a molecule CO NH3 4 times Cl2 all of plus, and this is in the form of a coordination, means in the form of an ion. Ready? The form of an ion. Fine. So what does it mean? The total charge of this entity is +1. The total charge of this entity is, the total charge of this entity is +1. Okay? Or in this entity, there are 2 different types of ligands. What are they? So you want to find the residual charge of the central atom. For that, you have to treat the ligands in a proper way. Okay. If ligands is there, or moreover, ligands always there. So you have to treat the ligands in a proper way. Then only obtain the residual charge on metal. Sometimes there may be Sometimes there may be counterions also. Okay. Here there is no counterion. Okay. Fine. So this is in form of a complex ion. The question is given in the form of a complex ion with a charge of +1. Fine. Both the ligands chlorido. This is chlorido, right? Yes. Chlorido, Cl have a charge of -1. Ready. Chlorine having a charge of -1. So 2 chlorines are there, so it will offer -2. Ready? And 4 ammonias. Each ammonia, which means a ligand amine, have 0 charge. So 4 amines offers 0. So it is very interesting to note that the answer is +1, but there is also a -2. So no doubt your cobalt should offer what? +3. If your cobalt offer +3, then only the +3 -2 become +1. Okay. So by treating the proper way, you obtain the residual charge. So cobalt is equal to +3. Ready? I'll give you another example. K4FeCN 6 times. So here counter ion is there. So if counter ion is there, then you consider the counter ion first. Okay. So actually that is potassium, and potassium belongs to first group, right? So a potassium can offer +1 charge. Actually there are 4 potassiums. So 4 potassium offer +4. Ready? If the counter ion offers +4, then your entity should offer -4. If your entity should offer if your entity is able to offer the -4, then that -4 is the sum of oxidation state of this central atom and ligand. Both the ligand is Cn. Cn is not neutral. Cn is a Cn minus. Cn is a negatively charged ligand. So this offer a charge of -6. This offer a charge of -6. Okay. So the whole charge of this entity is -4. The sphere is -4. Where in that your cyanide offer -6. If your cyanide offer -6 and the resultant answer is -4, then your Fe should offer +2. That's a simple mathematical logic. If -6 is here and you have to get -4, then the next component should offer +2. Ready? Fine. And if it was a complex ion, what will be the nature? ZnOH 4 times 2 minus. Okay. So it is clear that the whole charge is -2. Fine. What about the charge of OH? OH is a ligand called hydroxido with a charge of -1. So -1 into 4 is here. So that's equal -4. So already here is a -4, but the answer is -2. So no doubt your zinc have to offer +2. Okay. So this is how you can find the oxidation state. I'll give you one more example. Listen. PT NH3 twice Cl2 Hall means the charge of this complex is 0. If there is no charge mentioned in the complex, or if there is no counter ion, here there is no counter ion, right? Yes, but there are charge mentioned. Here is also no counter ion, right? But a charge mentioned. Here is a counter ion, no charge. Here is also a counter ion, so there is no charge especially mentioned. And this is a typical molecule. There is no counter ion, no charge, and that is said to be neutral complex compound, a neutral coordination compound. Fine. So if there is no charge or no counter ion, then the total charge of this molecule is said to be 0. Okay. If they mentioned it or not, usually they are not mentioning the charge of hold 0. Okay. We have to realize that the charge is 0. Ready? Fine. So hold the charge is 0. And so the total charge is 0. Okay, fine. The total charge is 0. Then what about the cases? Here, your chlorine offer -2 because chlorine have a -1 charge. Your amine offer 0. So here already a -2, but the answer is 0. So your platinum should offer +2. Okay, fine. So that is how you can find the oxidation state. Okay. You should be able to find the oxidation state, then only you can proceed the nomenclature or the entire molecules in this chapter. Okay, so this is very basic criteria. I'll give you more examples to find the oxidation state when I'm discussing the nomenclature. Okay, before that, there are some more important terms. The second important term, that is coordination number. Let the coordination number represented by abbreviation Cn. Let it be Cn. Coordination number Cn. Fine. So coordination number is nothing but it is a number of Number of coordinate bonds around central atom. Number of coordinate sigma bond around central atom. Okay. Total number of coordinate sigma bond around central metal. Around the central metal. That is said to be coordination number. Ready? Fine. So how can you find the coordination number? If I have 6 monodendrite ligands, then how many coordinate bonds to the central atom? 6. Because each monodendrite ligand can coordinate with a single, or each monodendrite ligand have a density 1. So 6 monodendrite ligand means 1 density and the number of ligands is 6. The total answer is 6. Now I have 3 bidendrite ligands. And you know that every bidendrite ligand can coordinate with the 2 bonds, or every bidendrite ligand can have a density of 2. So if 3 bidendrite ligands are there and one can form 2 coordinate bond, another one can form 2 coordinate bond, another one can form 2 coordinate bond, then what happens? There will be a 6 coordinate bond, right? Yes. So you find the answer in the way that number of ligands is only 3, where the density is 2. Then you obtain the answer 6. Okay. So it is very clear that how can you find the coordination number? The very same concept which is discussed in just last second. That is, coordination number is equal to what is the total number of atoms? You find the total number of atoms. I'm sorry, that is not atoms. Here it is ligands. What is the total number of ligands? And you multiply the total number of ligands with the density. Okay. Then you obtain the coordination number. Listen, I have example. CrH2O 6 times Cl3. Oh, the ligand is H2O. We have 6 H2O, right? 6 H2O. 6 H2O is a monodendrite ligand. So coordination number is H2O is a monodendrite ligand and number of H2O is 6. Well, the density is 1. So the coordinate bond will be 6, which means coordination number is 6. Okay. En thrice 3 plus. What are the charge? Here, the ligands are only 3. So coordination number is equal to number of ligand only 3. Number of ligand is only 3. So 3 into, what is the density? Ethylene diamine. En means ethylene diamine. The density is 2. So the answer is 6. Okay. Next, AlOX thrice 2 minus. I'm sorry. 3 minus. Well, the ligand is OX. What is OX? Oxalato. So what is the coordination number? Number of ligand is 3. Oxalato belongs to bidendrite ligand. So 2. So the answer is 6. Okay. Next, Ni DMG twice 2 plus. DMG is dimethyl glyoxime with a charge of -1, but the density is 2. So the number of ligand 2, density 2, the coordination number 4. Okay. The next is calcium EDTA, all of 2 minus. Where EDTA is a hexadendrite ligand, there is only one ligand. Where EDTA is a hexadendrite ligand. So number of ligand is only 1, but the density is 6. That is ethylene diamine tetraacetate. Fine. So the answer is 6. Okay. If FeCO 5 times, the ligand is carbonyl. Actually, carbonyl can also form multiple bond with the central atom. We will discuss that. That is said to be synergic effect or back bonding. But we are asked to find the number of sigma bond only. So the coordinate bond you have to consider. Okay, no need of considering the back bond or pi donation, etc. So coordination number is equal to number of ligand is 5. Where carbon monoxide is a neutral ligand with a density 1, so the coordination number is 5. So this is how you can find the coordination number. Ready? I'll give you one more example. These all are homoleptic complex, right? These all are homoleptic. Okay. I'll give you one example for heteroleptic. CONH3 twice En Cl2 all of plus. So this is a heteroleptic complex, fine. So we have two amines, two ethylene diamine, two chlorine, fine. So what is the coordination number? The number of first, you have to split up the ligands if you are given with a heteroleptic complex, okay? So the first one is amine, number of amine 1 with the density 1. Sorry, number of amines 2 with the density 1 plus the next, the number of ethylene diamine, there are only 1 but the density is 2. Next, chlorine, actually the chlorido actually 2 but the density is 1, so the total answer is 6. So if you have a heteroleptic complex, so you find the coordination number by splitting the whole, okay, and finally you add the whole category, so you obtain the number of coordinate bonds. So the total number of coordinate bonds around central atom is said to be what? Coordination number, okay. And I'll give you one more idea about the, or one more important term, and one more important term, that is coordination entity. Coordination entity, it is nothing but it's very easy concept. Wait, coordination entity, nothing particular, it's very easy. Coordination entity. Entity means a collective set is said to be entity. A collective group is said to be entity, right? So coordination entity means anything which enclosed in the coordination sphere is said to be coordination entity. You know what is a coordination sphere? Square bracket. So the whole, the square bracket is simply said to be coordination sphere. Square bracket come the species which are inside the coordination sphere, they are altogether called as coordination entity, okay. So it is the complete species in coordination sphere, okay, which means the coordination entity which consists of what? A square bracket, ligand, central atom, okay. And your coordination entity may be three types. It may be cationic entity. Your coordination entity may be three types. It may be cationic entity. If it is a cationic entity, then counterion will be anion. Counterions will be anions. If you have a cationic entity, then their counterions will be anions. And if you have anionic entity, your counterion will be counterions, cations. And if we have neutral entity, one more entity is there, neutral entity. If we have a neutral entity, then what is the difference means? No counterion. So there are basically three types of entities, okay. So the nomenclature mainly depends on the nature of entity, okay. So we'll discuss the nomenclature in terms of entity, okay. So you have to know what is, our next topic is nomenclature. Ready? Fine. So before that, the last important term, coordination entity. So cationic entity means an entity of charge what? This is belongs to a cationic entity. For the whole charge of the square bracket, all charge of this one, this is the entity group which is enclosed in the sphere. This is coordination sphere, and all together called coordination entity, where the charge of this coordination entity is positive, so that is said to be cationic entity. Okay, either the cationic entity represented in this pattern by mentioning the charge, or how you can find if there is no charge is mentioned, how you can find that is a cationic entity. If you have the counterion anions, here the counterions are anions. If the counterions are anions, then the charge of entity will be cationic. The charge of entity will be positive, no doubt. So the entity will be cationic entity. Is it okay? Fine. Here the charge of 3Br minus 3, so the entity plus 3. I think it is okay. So how you can find the cationic entity means either the entity Hall given by a charge of positive or the counter ion will be anion. Ready? And how you can find the anionic entity? That's the next idea. Either the anionic entity represented is in this pattern A log x thrice 3 minus where the charge is mentioned in on the top of that entity. Okay. Or it may be like this. Na3 COF6. Okay, what about the case? Here the counter ion. Here there is no charge in your entity. This is a neutral one. But the counter ion is sodium. Counter ion is cation. If your counter ion is a cation, then the charge is +3. If the charge is +3, then what is the difference? If the charge is +3, then your entity have a charge of -3. So if your counter ion part have a positive charge, then your entity part have a negative charge. Okay. And what about the neutral entity? Neutral entity is very easy. Well, the whole charge on the top of the element or top of the complex will be 0. Okay. Top of your complex is 0. That is will be neutral entity. Okay. Fine. Ready. So the residual charge of the complex or the entity is 0. So there is no need of a counter ion for satisfying that charge. Okay, so there is no need of counter ion. So that's all about the basic terms in your coordination compounds. So I think now you have an idea about the coordination compounds. And now we can move to the main important first section, nomenclature. Nomenclature of coordination compound. Put it as a heading, nomenclature of coordination compounds. So the next term is nomenclature. Ready? Or the next concept is nomenclature. So I'll give you a brief idea about the nomenclature, and in the next part we will discuss more examples about the nomenclature. Okay. So nomenclature, actually there are two different idea about the nomenclature. Okay. But the cationic and neutral entity have same kind of procedure, where the anionic entity is entirely different. Okay. Fine. So there are some steps or some procedure. So no need of finding the procedure. I'll teach you the procedure using example. Okay. Fine. The number 1 and the first nomenclature is for cationic and neutral entities. If your complex is either cationic, and you know how to identify a complex is cationic or not. Okay. And moreover neutral, cationic or neutral entity. So if you have a cationic or neutral entity, then how you can proceed the formula, or how you can write the nomenclature or find the nomenclature. Listen, let's discuss a molecule with a cationic entity, Ni H2O 6 times all of Cl3. So whether it is cationic or anionic, cationic, no doubt, because the counter ion is anion, right? Yes. So usually, listen here carefully. Usually, if you have a cationic entity, then your counter ion is anion, right? If your counter ion is anion, then it is on the right side. If your counter ion is cation, then it's on the left side. Okay. So if your entity is cationic, your counter ion is anion. Usually, the position of the counter ion is in the top right or extreme right. Okay. So what do you see from the left side? That is actually the entity, right? So if you're looking from here, what you can see? You can see the entity. Okay, so you simply enter to the entity. You simply enter to the entity. Okay. So in case of your cationic entity, you can see your complex, your entity first, then your counter ion. So you simply enter to the entity, and first you tell the name of ligand using multiplying prefix. Fine. Here only one type of ligand, H2O, and H2O, the ligand is said to be aqua, not water, right? We already know the names of ligand, which is discussed in the first part, right? So H2 is said to be aqua. H2 is said to be aqua. And what is the number of aqua here? Number of H2O here? There are 6 H2O are there, right? So we have to mention there is 6 H2O. We should mention that where there is like 6 H2O. So in order to mention 6 H2O, you simply say that hexa aqua. So like that. Hexa aqua. Which means that the aqua H2O ligand which present in 6 times, which present there as 6 times. Now you simply enter to the entity and name the ligand first. Now check or consider the central atom. Fine, the central atom is nickel, right? So next you say the name of central atom, nickel, and after the name of central atom, there will be you have to give a parenthesis. So, you have to give a bracket. Okay, where the oxidation state of central atom are represented in Roman numerals, which means stock. So you want to find the oxidation state. How you can find the oxidation state? Okay, how you can find the oxidation state that we already know. A chlorine have -3 charge, counterion chlorine have -3 charge. So your entity have +3 charge, where the charge of H2O is 0. So this +3, which is exactly offered by the nickel. So fine, it is clear that your nickel offer +3. Your nickel have a charge of +3. Ready? Fine. So hexa aqua, there is 6 H2O right there. Nickel. The charge of nickel, or the oxidation state of nickel in stock after the central atom. Oxidation state of central atom in stock notation after the central atom. Now this entity is over. Ready? Then simply leave the entity and consider the next portion. The next portion is nothing but what? That's actually counter ion. Okay, what is that counter ion? Chlorine. If chlorine is a counter ion, then it is said to be chloride. If chlorine is a ligand, then it is said to be chloridon. So here the chlorine is counter ion. Now you name the chlorine as a counter ion. So here the whole charge of each chlorine is Cl -1. So it is counter ion. It is said to be chloride. No need of mentioning the number of that counter ion. Okay. No need of mentioning the number of counter ion. You simply mention what? The number of ligands only. No need of mentioning the number of counter ion. Okay. You simply mention the nature of counter ion. It's just chloride. No need of trichloride. But you have to mention the number of ligands. That's very important. Okay, this is how you can name the complex. Okay. I'll give you another example. If I have a molecule PT NH3 4 times Cl2. PT NH3 4 times Cl2. All of 2 plus. So what is this category? This category is nothing but this is a cationic entity. So what do you see? What you can see on the first? You can see the first from the left. That's entity. So you simply enter to the entity and consider the ligand. Once you enter the entity, you have to name the ligand first. No doubt. So once you enter to the entity, fine, there is ligands, right? Yes. How much ligands? 2 different kind of ligands. Oh, if there are 2 different kind of ligands, then you have to name them in alphabetical order. Name them in alphabetical order. Ready? Fine. Which means this is a ligand called amine. This is a ligand called chloridon. So in your alphabetical order, your first one is amine. How much amines are there? How much amines? Actually 4 amines. So this is starting with the tetraamine. Now this is okay. Now the next. There are actually the ligand Cl minus. If your Cl minus is ligand, how you can identify whether it is a ligand or counter ion? Usually the counter ions are represented in the outside of the sphere, or the ligands are represented in the inside of the sphere. So that's perfect. That is ligand. If chlorine is ligand, then since there is 2 chlorine, you simply represent it as dichlorido. The ligand name of chlorine is chlorido. So ligands are over. Ligands are over. The next is central atom. Your central atom is platinum. Your central atom is platinum. Fine. Now you wanna show the oxidation state of platinum. For that, you have to find the oxidation state. The Hall charge of this entity is plus 2. Where we know that 2 chlorine offer minus 2, or amine offer 0. Since here is a minus 2, for obtaining plus 2 on the outside, this should be plus 4, no doubt. So that's a simple logic. So platinum plus 4. And the Hall is an ion, right? Whatever it may be, say monatomic ion, polyatomic ion, whatever it may be, it is a complex ion. This is nothing but this category is an ion. Okay, so you simply add ion on the terminal length. Ready? Fine. Now, how you can name a neutral entity? A neutral entity. PT, NH2, Cl2. This is a neutral entity. Both the nomenclature of cationic and neutral entities are alike, which means similar. Ready? So, to name a neutral entity, what's the difference? Listen. In case of your neutral entity, there is no counter ion on the left or right. Okay, so you can see what entity. So you simply enter to the entity and name the ligands in the alphabetical order. Fine. 2 amines are there. So diamine. Okay, diamine, dichlorido, platinum, diamine, dichlorido, platinum. Now you want to return the oxidation state. Fine. Here is 0, right? In case of neutral entity, the Hall charge is 0. If the charge is 0, it will not be mentioned. So Hall charge is 0. Here it is minus 2. Amine is 0. So since here is a minus 2, to obtain the 0 as the answer, your platinum should offer plus 2. So the oxidation state of platinum is 2. Since this is not an ion, this is a neutral molecule, so no need of writing ions like in this case. Okay, I'll give you another example. Have another molecule, CO, NH3 thrice, NO2 thrice. This is a neutral molecule. The Hall charge is 0. So you simply enter to the entity. Now, amine, nitrito, N. These are the ligands. Amines and nitrito, N. So there are actually 3 amines. So, triamine. 3 nitrito, N. It's not nitrito. Nitrito, N. Further. Nitrito, N. So, triamine, trinitrito, N. Now, your central atom, fine, that's cobalt. Usually, the species which are enclosed in the square bracket, which means the coordination entities, which means ligands plus central atom, they all written without any space. The space may create in between the counter ion and coordination entity. So anything which enclosed in a coordination entity are usually written without space. Okay, ready? Fine. So you should write this in this pattern, but you are dealing objective questions, so there is no problem because the names are already given the choice. So you simply look at the molecule and choose the choice. Okay, fine. So what about the charge? Cobalt, Hall charge is 0 because neutral. NO2 have a charge of minus 1, right? So 3 NO2 means minus 3. Amine 0. So this cobalt should offer plus 3. Is it okay for you? Yes. Okay. So this is how you can write the name of what? Write the name of the nomenclature of what? Cationic and neutral entity. Okay. One more case is there. Listen. One more case is there. If I have a cationic entity like this, CO, En, thrice, all of Br3. Okay, fine. So it's a cationic entity because the anion is counter ion is anionic. So you simply enter to the entity because your first one from the left is entity. So while you are entering to the entity, you want to name the ligand first. What is that ligand? En, ethylene diamine. Ethylene diamine or ethane 1,2-diamine. They are named in this pattern either ethylene diamine, this is a common format. Ethane 1,2-diamine is the IUPAC format. Both are accepted. Ethane 1,2-diamine, both are accepted. Ready? And the abbreviated as EN. So EN means ethylene diamine. So listen here. In this molecule, the name itself have a multiplying prefix di, right? In the molecule, the name itself have a the ligand name itself have a multiplying prefix di. Agreed? Agreed? Yes. So, if the name of ligand itself have a multiplying prefix di, try like that. If so, then the number of ligands or the number of ligand multiplying prefix are represented by either by bis, tris, tetrakis, pentakis like that instead of di, try like that. Okay, I'll explain that. That is, here the name is actually 3-ethylene diamine, right? So ethylene diamines are how much? 3. So in this name of ligand, there is a multiplying prefix. So you have to write this as tris-ethylene diamine. It's not tri. This is the correct one. Not tri-ethylene diamine. Tri is not accepted here because in this ligand name there is already a multiplying prefix. If there is some kind of multiplying prefix which is in the name of which are already in the ligand names, then you should add the multiplying prefix of ligands using, if it is di, then you should convert it as bis. If it is tri, then you should convert it as tris. Tetra, if you want to write tetra, but you have to write tetrakis, pentakis like that. Now, actually there are 3 ethylene diamine, right? So usually I am writing tri-ethylene diamine, but it is wrong because there is a di multiplying prefix already in the ligand name. So you should use tris. Instead of tri, you should use what? Tris. That is a rule. So this is wrong, this is correct. So tris-ethylene diamine, now this is over. What is over? Ligand name is over. And moreover, one more thing is that if you are using bis, tris, tetrakis, pentakis, then it is very better to write that ligand name within a parenthesis. Within a parenthesis. Tris within a bracket, ethylene diamine. Now the ligand is over. Now central atom. Central atom is cobalt. Cobalt. Now you want to find the, you want to write the stock notation. So 3 bromines can offer -3. So this central cobalt can offer +3. The charge of ethylene diamine, which already discussed, that is 0. So the +3, whole +3 charge is simply offered by your cobalt. So the cobalt which is in +3. And finally, now this is over. The next, your counter ion. Counter ion, you have to mention the nature. No need of number. It's not tribromide. It is bromide enough. Okay, fine. I'll give you one more example regarding this one. Wait, then it will be clear for you. Listen. If I have a complex PTEN twice Cl2, all of +2. Okay, listen. So I'm simply entering to the entirety. The ligands are ethylene diamine chlorido. Ethylene diamine starts with E, chlorido starts with C. A, B, C, D. Oh, C is the more alphabetically preferred. So you have to show the C first. It is dichloro. Now this ligand is over. Now you wanna write the name of ethylene diamine. Actually, there are 2 ethylene diamine. So di-ethylene diamine is wrong. Bis ethylene diamine is the correct one. I think you are okay with that because the ethylene diamine, very same ethylene diamine have a multiplying prefix in the name itself. So you wanna show the multiplying prefix of that ligand using bis instead of di. So di is wrong, bis is correct. So bis ethylene diamine. Now these all are over. The next central atom, that is platinum. Platinum, you wanna find the oxidants here. Here it is +2. So this is -2. This is 0. So this should be +4. Sorry, stock notation of 4 is like this, and this is an ion. Okay. And one more thing is that usually the first letter is capital, the rest remaining are in small. Okay. So we'll discuss more examples. Before that, this is a trend of naming of what? Neutral entity and cationic entity. And there is a small difference in the nomenclature of anionic entity. In the next part, I'll explain that difference, and we will discuss more examples. Okay. If more examples are discussed, then we can move to the theories of coordination compounds. There are some kind of theories like Werner theory, Sidgwick theory, valence shell electron pair repulsion, VBT theory, valence bond theory, and the most important crystal field theory. Okay, and some isomerisms and applications of that. These are the concept in your chapter. And isomerism, that's a very important section, structural and stereoisomerism. Okay, we'll discuss that. So the next is the nomenclature of anionic entity.